Let's jump right into this explainer by tackling a super common illusion we all kind of fall for when writing scripts. There's this quote: Python is often perceived as a language in which everything happens by itself. I mean, it's true, right? You write the code, you hit run, and boom, magic happens. It feels totally effortless. But as we're going to see, that perceived simplicity, it's actually hiding a seriously sophisticated, multi-stage transformation process under the surface.
So today, we're unmasking Python. We're peeling back the layers of its execution mechanism to really understand its architectural bottlenecks and, honestly, its incredible power. We're going to look at what Python is actually doing under the hood, why it historically gets a bit of a bad rap for being sluggish, and how it somehow manages to completely dominate heavy-duty computing across the globe anyway.
To get to the bottom of all this, we first need to answer one seemingly simple question that kicks off the whole shebang. What exactly happens when you click Run? You type your script command into the terminal, and execution doesn't just start instantly. No way! There's this hidden, lightning-fast preamble happening before your logic ever even sees the light of day.
Here is our roadmap for the explainer. 1. Hitting run and the code's journey. 2. Inside the virtual machine. 3. Why Python is slow. And 4. The secret of its speed.
All right, let's start with section 1. Hitting run and the code journey.
The absolute millisecond you execute a script, your perfectly formatted code takes a 3-step compilation journey. And yeah, you heard that right. Compilation. Even though Python is famous for being an interpreted language, it actually does compile your code first. Step 1 is tokenization, or lexical analysis. Basically, this is where your code gets chopped up into the smallest meaningful pieces, tokens, like keywords, variable names, operators, and brackets. Next up is parsing. The interpreter grabs all those tokens and organizes them into an abstract syntax tree, or AST. This tree structurally maps out the logic of your program. If you missed a colon or messed up your indentation, well, the AST is going to catch those syntax errors right here. Finally, step 3 is compiling that AST into bytecode. The compiler traverses the tree nodes and translates your human-readable logic into low-level instructions.
Now, the really crucial point here is that this bytecode isn't raw machine code yet. It's a low-level set of cross-platform instructions acting as a pre-compiled intermediary. It doesn't care about your specific processor or your operating system. It's specifically designed just to be read by Python. And here's a fantastic little optimization trick. Python saves this bytecode into a hidden cache directory, usually as .pyc files. It does this to make your next run even faster. If you haven't touched your source code, Python completely skips the heavy lifting of tokenizing and parsing and just loads that cached bytecode straight away.
Moving right along to section 2, inside the virtual machine.
So, your bytecode is ready, but it obviously needs an environment to run in. This is where the bytecode gets handed off to the PVM, the Python virtual machine. This is the true heart of the interpreter. The PVM is essentially a stack interpreter that sequentially reads and executes those bytecode instructions. Think of it literally like a physical stack of plates. If you're adding two numbers together, the PVM pushes the first value onto the stack, then pushes the second value right on top of it. Then it triggers an addition operation which pulls both of those numbers off, does the math, and slaps the final result back on the top of the stack for whatever instruction comes next. It's incredibly systematic.
But what's really fascinating here is that the PVM doesn't actually do all the heavy lifting itself. It's more like a really great manager. For everyday operations, say list concatenation or running basic math, the PVM delegates that work to highly optimized C functions for memory efficiency. When you call an append method on a list, the PVM isn't out there struggling through memory management at the Python level. Nope, it turns to a C function that directly and efficiently handles the memory for you.
Which brings us to section 3. Why Python is slow.
Now, you might be wondering, if Python relies on fast C functions, why on earth do developers constantly complain about its speed? Well, when you contrast Python's layered architecture with the direct-to-hardware approach of languages like C or C++, the structural bottleneck becomes pretty obvious. In C or C++, your source code is compiled directly to machine code. It interacts with the hardware instantly. Python, on the other hand, is compiled to bytecode and requires that entirely separate abstraction layer, the PVM we just talked about, just to execute. That extra translation layer fundamentally adds latency.
The actual reasons Python is inherently slower really come down to 4 specific architectural choices, which basically force the interpreter to do a massive amount of checking and locking on the fly. First up is dynamic typing overhead. In C, a variable's type is strictly known during compilation, but But in Python, every single time you execute an operation, the interpreter has to stop and check its validity at runtime. Second is interpretation itself. Processing bytecode at runtime without a default just-in-time compiler slows things down. Third is the GIL, which we'll dive into in a second. And fourth is automatic memory management. Python runs garbage collection in the background to automatically free up resources, which, don't get me wrong, is incredibly convenient for us developers, but it absolutely demands extra computational costs from the machine.
I really want to highlight that third point, the GIL, or Global Interpreter Lock, because while it keeps memory management perfectly safe, it's a huge bottleneck. It's literally a lock allowing only one thread to control the Python interpreter at a time. You could be working on an absolute beast of a machine with 32 cores, but standard Python is still going to enforce this lock, ensuring only one single thread can execute Python bytecode at any given moment. It's a massive roadblock for parallel computing.
All right, moving to our final section, Section 4. The secret of speed. This brings us to a massive paradox. If Python is so slow, why are libraries like NumPy, Pandas, and TensorFlow so incredibly fast? How can a language completely hampered by locks, constant runtime checks, and heavy interpretation layers serve as the absolute backbone for data science in machine learning?
The answer? Python achieves blistering speed through delegation. It pushes heavy calculations down to highly optimized C, C++, or Rust libraries. This is the ultimate cheat code. When you ask NumPy to sum up a massive array, Python isn't doing the math, it passes it off. Plus, it uses vectorization. Instead of using a painstakingly slow Python for loop to process millions of items one by one, it processes whole arrays simultaneously. And finally, these libraries enforce minimum type checks by using fixed data types like float64, entirely bypassing Python's slow dynamic type checking on the fly.
The ultimate takeaway of this explainer is that Python is a carefully balanced trade-off. It actively sacrifices raw execution speed for developer speed. It writes fast, while compiled code does the heavy lifting in the background. It allows you to build out complex architecture seamlessly, write code rapidly, and deploy across any operating system, all while incredibly fast compiled code operates silently under the hood. It really is a brilliant hybrid architecture.
I want to leave you with a final thought as you consider why this layered, paradoxically slow architecture has become literally one of the most dominant forces in tech today. With Python ruling everything from web backends to AI, ask yourself, in modern software engineering, what is ultimately more valuable? The speed of the machine executing the code, or the speed of the developer writing it? Thanks for exploring the inner workings of Python with me today on this explainer. Keep learning, and I'll catch you next time.